Okay, so in this lecture, we finally make it to the singular value decomposition. But before getting to that, let's recall a few notions from last lecture. So what would be the first one? So if a matrix S is symmetric with positive eigenvalues, then S can be factored as Q lambda Q transpose, where Q is orthogonal, meaning the columns are orthogonal and have unit length, so orthonormal columns, and lambda is diagonal. So this is like a special case of eigenvalue decomposition when we have the symmetric matrices. Okay. What else did we learn? So not all matrices have eigenvalue decompositions. In particular, these rectangular matrices and a lot of the square matrices as well. And then one more fact that I said last lecture that I didn't spend too much time on. I'll probably give you some reading to look at this on your own. But that is that orthogonal matrices can be thought of as rotation matrices. Or rotation. So if you apply an orthogonal matrix to a vector, it's going to rotate it and reflect it in space, depending on how many dimensions you're in. Okay, so now in general, we're not going to have, as this second bullet point notes, if you have an M by N matrix, you're not going to have an eigenvalue decomposition. But we want something as close as we can get to this, right? How can we mimic this? So, so let's just say let A be M by N. Okay. And then what do we want? We want something like the following. A times B1 equal something called sigma times U1, A times B2 to equal something like sigma 2 times U2, dot, 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 A times BR equal to sigma R times U R, where R is the rank of the matrix A. It's the number of linearly independent columns. Okay. So we want this, and also almost forgot really important fact where V1 dot dot through VR and U1 dot dot through UR are orthonormal collections of vectors. Okay. And so that's an orthonormal set, and this is an orthonormal set there. So these and U's, they're different. It's not like over here with this eigenvalue decomposition where we have Q's, lambdas, Q's, we have V's, sigmas, and U's. Okay, so this is what we want. We want, because this is like a system of equations way of saying something similar to this, right? Like just to be clear, if you forgot what the eigenvalue decomposition did, if I multiply, let's say Q on both sides of this equation, I get S times Q is equal to Q times lambda. S times Q is just saying S times Q1 is equal to eigenvalue 1 times Q1, Like if I multiply both sides by Q, orthogonal matrices, the transpose is equal to the inverse. That was like another important point maybe. Orthogonal Q implies Q inverse is equal to Q transpose. So if I multiply both sides of this equation by Q transpose, no, by Q, I'll have SQ is equal to Q lambda, which gives us a system of equations that kind of looks like this. So we're trying to mimic that. We want to figure out if we can somehow factor A to mimic the eigenvalue decomposition that we discussed last time. So in matrix form, this looks like A times B1 through BR equals to U1, these are all column vectors, UR times sigma 1 on the diagonal, sigma R, and there's zeros everywhere here. Like that. So, of course, the matrix representation is easier to look at here. So if we multiply, so this is just saying A, V is equal to U, we'll call this capital sigma. And since V is a collection of orthonormal, it's an orthogonal matrix, if we multiply by V transpose on both sides of this equation, we get A is equal to U sigma V transpose. So this is what we want. We want something that looks like that. Okay. So how can we do this? Well, we're going to work backwards to get to this, to find out, like, so the question we should have immediately, what is U? What is sigma? And V transpose. So what are those things, right? What are the vectors that go into the U? What are these vectors that we're choosing here? What are those sigmas? What are the U's? In order to figure out what those are, we're going to work backwards from what we want and figure it out after the fact. So it's supposing that A has this form, A transpose times A is going to be this all transpose times the same factorization. And again, we don't know what U, what sigma, what V are yet. We're going to find out in a moment though, because if you recall, we know something about A transpose A. It's going to be a symmetric matrix with positive eigenvalues. So it's going to have a factorization, which will tell us what the U's and the B's will be once we kind of simplify things out. So what does this become? So the transpose of all this is like B transpose transpose, which is just B, times sigma transpose times U transpose, times U times sigma times B transpose. Right? You just, whenever you take the transpose of a product, you just flip it, right? So you have A, B, C, all transpose, that's going to be C transpose, B transpose times A transpose. Just always remember that. Okay, so now notice that U transpose times U, well, U is an orthogonal matrix, which means that the transpose is the inverse. So U transpose times U, this is just the identity, that goes away. What are we left with? Ah, that looks familiar. We have orthogonal matrix, and diagonal times diagonal is going to be diagonal again. So this is still a diagonal matrix. This is going to be an n by n symmetric matrix, right? With positive eigenvalues. We have orthogonal times diagonal times orthogonal transpose. Orthogonal times diagonal times that same orthogonal transpose. And we just learned something. We learned that this can be thought of like Q lambda Q transpose, the eigenvalue decomposition. Or eigenvalue diagonalization. I call it decomposition. So look, we can match it up. We can say, so what that means is these two things together tell us that B is equal to Q from A transpose times A eigenvalue decomposition. And also that sigma times sigma is equal to lambda. What this is saying is that basically the square of the sigma I needs to equal the eigenvalue I. That's what that sigma times sigma is saying. We're going to let it equal that the eigenvalues. Okay. All right, but what about the U's? How do we find the U's? Well, we can use the same trick. Just now look at the M by M matrix, A times A transpose. So this is going to be U sigma B transpose times U sigma B transpose transpose. So we have U sigma B transpose. V transpose transpose is just V times sigma transpose times U transpose. B is a orthogonal matrix, so that's the inverse of itself. The transpose is the inverse, so that goes away, and we're left with U sigma transpose U, where U is a orthogonal matrix. Sometimes you will hear people say unitary instead, but we don't have to worry about that. But here, oh, U is equal to Q from A times A transpose. Right? Notice that A transpose times A is a different matrix than A transpose. This is N by N, this is M by M. Right? But if we look at the eigenvalue decomposition of A times A transpose, the orthogonal matrix that we get from the eigenvalue decomposition, we can set that equal to U. That's orthogonal, that's diagonal. It's going to work out. So, what did we just learn? We're not entirely finished yet, but we're close enough. We can factor A into such a factorization where maybe I should save room and say where the singular, so these are called singular values. Where the singular values equal the eigenvalues. So the singular values squared equal the eigenvalues from the eigenvalue decomposition of A transpose A. Maybe I should write that out instead of doing this, because there's an ordering that we're going to put on these things. So where the singular values in sigma are the square roots of the lambda. So if you just square root both sides, you'll get, are the square roots of the eigenvalues of A transpose A, or A transpose. It doesn't matter. They're going to be, it's all going to be the same. Okay. What is U? U is the right. U contains the right the left singular value. Sorry. U contains the left singular vectors which are the orthonormal vectors from the eigenvalue decomposition of A transpose. So left singular vectors, which are the orthonormal vectors from the eigenvalue decomposition of A times A transpose. There's lots of writing here, but this is what it is. V contains the right singular values, or the singular vectors, which are the orthonormal vectors from the eigenvalue decomposition of A transpose A. This is the SVD, the singular value decomposition of the matrix A. Every matrix has one. Unlike eigenvalue decompositions, where only special matrices, these symmetric with positive eigenvalues, have these very special eigenvalue decompositions. Every matrix has a singular value decomposition, regardless of its shape. Okay. So what should I say? The ordering of the vectors in U and V transpose. All right, so sigma, first off, the singular vectors, sigma 1 dot u sigma r. And again, R is the rank of the matrix. It's the number of non-zero. I mean, it's the number of linearly independent columns. Let me make sure about something real fast. Yeah, it's fine. So these singular values are listed in non-increasing order. So the top singular value is the largest, the second singular value is the second largest, and the vectors, the corresponding singular vectors in U are listed in the same way. So U1 corresponds to sigma 1, U2 corresponds to sigma 2, so forth and so on to UR. That's how we write out U. See, U. And then the same thing with V. Okay. Okay. So now that we have that, that's more or less the decomposition we want. And it's based off of really the eigenvalue decomposition of AA transpose in A transpose A. Not how you would compute it in practice typically. You would not want to multiply two very large matrices together for several reasons. So in practice, the packages that you'll use to do this in Python or Julia or MATLAB will not do A transpose eigenvalue decomposition of that. There's other ways to do this. But for our purposes, by hand for small HCs, that's how we'll do it. But so what are these doing? Like, why am I so concerned about this? This decomposition. So is there maybe a geometric interpretation? Because we know that when you multiply a vector by a matrix, it will take it somewhere else in the plane, for example, for an R2. We also know that orthogonal matrices can be considered rotations and reflections in space. This is orthogonal, that's orthogonal. And this is just diagonal of scalars. So diagonals of scalars are just going to stretch the vector. So what we have here is, we can think of this as like rotation, stretch, rotation again. Or actually, we'd be multiplying a vector over here. So we'd rotate, stretch, and then rotate if we multiply the vector. Okay. So there is a geometric interpretation for this. So maybe we should calculate one by hand and see what it does in like two-dimensional space. See if I have any examples. Oh, these examples look so boring. For one moment. I guess we'll just do like a super simple one real fast. There has to be a reason why this textbook I'm using has this as like an example to do. I don't know. Okay. So we're going to need to look at A transpose for sure. So the columns of A become the rows of A transpose. So column 2, 0 will be 2, 0. Column 0, 3 will become 0, 3. So A transpose times A is equal to A transpose. So it's symmetric. That's why did they choose this matrix? Because it's symmetric, we could really just do the eigenvalue decomposition, but let's do the SVD. So then A transpose times A 2, 0, 0, 3 times 2, 0, 0, 3. All right, so what's in the first row? It's 2 of this column plus 0 of that column, so it's 4, 0. What's in the second column? 0 of that column plus 3 of this column, so 0. All right, it's just like squaring it, right? So now we need to calculate the eigenvalues of A transpose A and the eigenvectors so we can get our V's and our U's. So to do that, we're going to have 4 minus lambda, 9 minus lambda, 0, 0, determinant. So we get 4 minus lambda times 9 minus lambda. This is all set equal to 0, by the way. Okay. What do we get? So 18. So I guess like 36, and then minus 4 lambda, minus 13 lambda plus lambda squared is equal to 0. So then, oh, what am I doing? Why did I even do that? That's dumb. I wasn't thinking. We can see the lambdas immediately. 4, 9. Okay. So we know this. That's why they chose this matrix, because the square roots of those will be the singular values. So we know the singular values immediately. Sigma 1 is going to be the square root of that, which is 3. And sigma 2 is going to be the square root of that, which is 2. All right, so now we need to find, so which ones do we get from A transpose A? We get the vectors from B. So, so the eigenvalues were 9 and 4. So we have to look at this and subtract off 9 and 4, and then find the vectors, right? So I'll do lambda equals 9 first. So 4 minus 9, so minus 5, and then 0, 0, 0. So oh, X is in the null space. There's only one, right? If we subtract off 9 there, it's 0. We subtract off 9 there. Yeah. There's only one solution to this. X is equal to 0. And the same thing's going to happen for the other eigenvalue, right? Because we know, what do we know? We know A minus lambda I and X is equal to 0. Right? And we do have the right eigenvalues, because look at the trace, right? 9, 4, 9, 4, everything adds up correctly. So we know that we're seeking solutions for this, right? So, oh. That's what the eigenvalues of that matrix and the eigenvectors. There's A transpose times A. So, by the way, since it's symmetric, A times A transpose is going to be the same. We're finding the U's and the V's at the same time. But what's bothersome here is that if I do 4 minus 9 and 0, 0, 9 minus 9 times x1, x2 equal to the 0 vector. 4 minus 9 is, minus 5 and 0, 0, 0. We get a row of zeros here. And actually, it doesn't have to be the 0 vector. It could be 0, 1, and that's fine. So let's just do that. Maybe I was overthinking it. 0, 1, right? 0. So 0 of this column plus 1 of that column. I said I was tired earlier. I didn't realize that the 0 vector wasn't the only solution. And this has unit length too, so that's good. And that one corresponds with eigenvalue 9, and then for eigenvalue 4, we'll have 0, 0, 0, 5. And then you can just do 1, 0, and that's also, this would be 1, 0. All right, so because these are going to be the same for A times A transpose, we have our vectors for V and U, and we have our singular values 3 and 2. So the singular value decomposition would be, so this is the largest, this is our first U, 0, 1, 1, 0, times 3, 2, 0, 0, times so this column becomes the first row. Yeah, it's gonna be symmetric. This column becomes the first row. So this is U sigma E transpose. It's so silly for this one matrix. That's why I was kind of hesitant to do this one. But maybe this will help us understand the geometric interpretation that I was trying to get at as rotation, stretch, rotation. So let's look in let's look at the unit vectors here. So this is like maybe V1, V2, and they're just unit vectors. Okay. So what happens when we multiply these unit vectors by V transpose first, right? So 1, 0, 0, 1. That's V, and this is, so that's V1, V2. Actually, I shouldn't use V. W, so you don't get confused. W1, W2. They're just the unit vectors 0, 1, 1, 0, 0, 1. So what happens when we multiply by A? Well, we can factor A into these pieces and then do one at a time. So what's the first one? The 0, 1, 1, 0, and 1, 0, 0, 1. It's going to be a matrix. So 1 of this column plus 0 of this column. So you have 0, 1, 0 of that column plus 1 of that column, and you have 1, 0. So it just took, this was our input, and now it's this. So where did it take W1? W1 is now at 0, 1. So W1 is now up here. And so it's like been moved over here. And then W2 is at 1, 0. W2 is now here. So basically switched them, right? Like rotated around somehow and switched them. Yeah, rotated this vector up and that vector down. Okay, so now let's multiply by sigma. This what the output. So sigma is 3, 0, 0, 2, 0, 1, 1, 0. Right? So it's 0 of this column plus 1 of this column. So 0, 2, 1 of that column plus 0 of this column. So 3, 0. So notice now that W1 is now being stretched by 2. So W1 moved there, and now it's being stretched out. And W2 rotated there by the V, and then was stretched by 3. And then finally, multiplied by U, this output. And so 0 of that column, 1 of that column, 2 of that column, so 2, 0. 3 of that column plus 0 of that column, so 0, 3. So now, where did W1 get sent back to? So W1 is here, and now it's there. So it rotated it back down here, and W2 is now at 0, 3, rotated up there. So in any case, you're forming what are called hyperellipses. Like the rotations belong to some, for a given set of perpendicular angles, the rotations belong to some ellipse. They're all, the unit vectors are rotated, then they're stretched in different directions. Like W2 is stretched 3 this way, W1 is stretched 1 that way. Okay. So and the stretching aspect is actually important. And we'll get to that. Time is it? In a moment, maybe. Okay. So, what does the stretching have to do with data? What does the stretching have to do with data? What does the factorization have to do with data? Well, it's because of the following fact. Let's see. What could we say here? I might even have it pulled up on my computer right now. I'm just checking something. 1 second. Let me see. I think the first thing I want to say is that we can use the factorization to approximate the original matrix. Now with this little bitty matrix, it's not going to be easy to do. Can I? Let me see. I'm looking to see if I have an example. I'll just show you. How about that? It's not going to make much sense for these small matrices. Okay, so let me pull up my screen. Okay, so this is my preferred linear algebra programming language. It's called Julia. And I want you to take a look at this image here. Okay, it's a grayscale image, which means it's a matrix where each entry is between 0 and 1. Okay, the closer to 1 the image is, the lighter the image, the pixel is. So the closer to 1 the cell is, the closer that pixel is to being white. Okay, so it's just a matrix, that matrix, see? Okay, so I'm going to go ahead and compute the SVD here. And again, you don't need to know any of this code. This is Julia, this is not Python. And the SVD does exactly what we just did for this big matrix here. And then notice the singular values, right? This is the largest one, next largest, so forth and so on. So what's going on here? Well, this is what would be called a rank 2 approximation to the picture, to that matrix actually. Rank 2 meaning we have linearly independent U's and V's, and we take 2 of them, so the rank of the matrix that we result in will have rank 2. So if I take the first 2 columns, multiply that by the sigma matrix 1, 2 to 1, 2, and then multiply that by the first 2 rows of V, look what it spits out. Now think about that. This is a 512 by 512 matrix, and we're able to somehow view it, if we convert the matrix back to a picture, just by using the first 2 singular vectors and singular values. What about if we use the first 10 singular vectors and singular values? This is what the resulting matrix will look like once you convert it back to a picture. What about the first 20? First 30? 40? 50? 100? That's basically good enough for me. Like, look at that picture, and then look at the original picture. You see how, so why would this be important? Well, we just compressed that image. That image was 512 by 512, and we're only using 100 row vectors here, a square 100 by 100 matrix, and 100 column vectors. And this matrix here, we don't even need the matrix. We only need the singular values, which means that we're only storing 100 numbers instead of 1,000 entries. So it's like 100 numbers, 100 vectors, 100 vectors. So it's really like we're storing basically a 100 by 100 matrix instead of storing a 512 by 512. So for very high pixel counts, like you're thinking about like 4K, 8K pixels, like for a picture, where it's like 8,000 pixels instead of just 512 or 512. And they could be like color, like you could have RGB coloring, right? That could be a very expensive thing to store and manipulate in a computer. But if you compute the SVD, you can store that image at a lower cost in your computer and manipulate that image at a lower cost. Okay. So the main point that I'm getting to is that the technicals you'll learn in advanced linear algebra and optimization, but I'll just say this right now. Using the first K vectors in U and V together with the first K singular values. Gives the best approximation to A with rank K. So among all matrices with K linearly independent columns, or rows, it doesn't matter, columns, among all possible such matrices, if you look at the norm between A and, I'll denote this UK, sigma K, the transpose K. So using the first K columns, first K singular values times the first K rows, among all of those in norm, so or in other words, the distance from A to this matrix is less than or equal to the distance from A to B for all matrices B with rank K. Whenever I say rank, again, it's the number of linearly independent columns of that matrix. And for all matrices B with rank K. That's important. That's why that picture looks the way it does. Right? When I use the first 100 columns, 100 singular values, and 100 rows, I had a rank of 100 matrix that basically was A. When we looked at the image after we converted it back to the picture, it basically looked like the image generated by A. And it's because among all possible matrices, this one is closest to that matrix by using those singular vectors and singular values. Okay. Now that's one thing that's really nice. Okay. What we'll learn about tomorrow on the last day of class. Is it tomorrow last day? We have still 2 days. Yeah, tomorrow's the last day. We'll learn how we can use the singular value decomposition to select the best features from a given data set of features that you want to run some machine learning model on. We'll also learn how we can cluster data using this decomposition. More or less, the idea is to take your data matrix and for each row, replace the entries by standard deviation or variance. And then when you look at the singular value decomposition, the vectors u and v are going to u1, u2, v1, v2, well, u1 in particular, are going to stretch in the direction of most variance where your machine learning model should probably train on. So that's where we're going for tomorrow. As far as what you can do in the meantime. I would say read string 7.3 before next class. All right, and that'll be it for this lecture.